Everyone knows the dinosaurs ruled the Earth, but what if I told you the true apex predator appeared 40 million years before the first dinosaur? In the early Permian, roughly 295 to 272 million years ago, Dimetrodon dominated swamps and floodplains. It carried a sail up to 5 feet high on its back and armed jaws with teeth that cut flesh like serrated knives. It wasn't a dinosaur, it was a synapsid, an early branch of amniotes that would eventually give rise to mammals, while dinosaurs came from a very different line. And that distinction is where the confusion begins. Most people still imagine Dimetrodon sharing the same world as Tyrannosaurus rex, as if one sail-backed creature prowled alongside the most famous dinosaur, but the truth is quite different. Dimetrodon lived during the early Permian, roughly 295 to 272 million years ago. Dinosaurs wouldn't appear until about 230 million years ago, creating a gap of more than 40 million years. That kind of separation is hard to picture, but it makes clear that Dimetrodon never crossed paths with a single dinosaur. Rather than a reptile on the road to extinction, Dimetrodon belonged to an entirely different branch of life. It was a synapsid, a lineage more closely related to mammals than to dinosaurs or modern reptiles, though not a direct ancestor of mammals themselves. Seen in this light, it wasn't a dinosaur stand-in, but part of a parallel story unfolding long before the age of dinosaurs began. Its role in evolutionary history was unique, with traits that hinted at possibilities mammals would later expand upon. One obvious example lies in its very name. Dimetrodon means 2 measures of teeth. Unlike many primitive animals that carried simple rows of identical teeth, Dimetrodon had different tooth shapes, incisor-like cutters at the front, massive canines for piercing, and smaller cheek teeth for slicing. That feature, called heterodonty, was an advanced step toward the specialized teeth seen in later mammals. Outwardly, Dimetrodon looked reptilian, scaly skin, sprawling limbs, a long tail, but its inner design told another story. Fossils reveal a skull with a single opening behind each eye socket, the temporal fenestra, which housed large jaw muscles. This gave it stronger bites compared to its early reptile relatives. Dinosaurs and modern reptiles, by contrast, belong to the sauropsid clade and typically show 2 such openings or none at all. That subtle difference in bone architecture was not trivial. It marked a deep evolutionary divide between 2 great lineages of land vertebrates. Misunderstandings about this divide date back to the early days of paleontology. Fossils like Dimetrodon were once labelled mammal-like reptiles, a phrase that lingers in old textbooks and displays. Today, we know this description is misleading. Dimetrodon was not a reptile at all, but a synapsid occupying a branch of the tree that would produce mammals separate from the sauropsid branch that produced dinosaurs, crocodiles, and birds. Placing Dimetrodon on the timeline sharpens the picture even more. The distance between it and the first dinosaurs is greater than the span that separates humans from Tyrannosaurus. Think about that. We live closer in time to the world of the great theropods than dinosaurs ever did to Dimetrodon. It breaks the familiar childhood scene of all prehistoric giants lumped together on the same landscape. This is what makes Dimetrodon stranger than simple reptile comparisons suggest. It had the look of a reptile, but the architecture of a synapsid. It carried advanced teeth and jaws tools, hinting at directions evolution would revisit millions of years later. Understanding that identity helped set the stage for what really made it remarkable, not just its lineage, but the way it rose to the very top of its ecosystem as a formidable predator. Picture the early Permian lowlands. Swamps and river margins stretch across the landscape, dotted with ferns and primitive trees. Amphibians like Eriops loaf near the shallows, while smaller creatures such as Simoria scurry between patches of vegetation. In this setting, one predator rules above all others, Dimetrodon, the undisputed apex hunter of its time. Adult Dimetrodon reached impressive proportions, about 11 to 15 feet in length, with body mass estimates ranging widely between 130 and 550 pounds. By the standards of the early Permian, this was a giant. Its bulk gave it presence, but dominance came from more than size alone. Dimetrodon used strength paired with precision, and that combination made it a master of its environment. The world it inhabited was packed with prey. Rivers carried large amphibians, and the floodplains supported early reptile-like herbivores. To exploit this variety, Dimetrodon needed more than brute force. Its skull and jaws were built for sudden, crushing strikes, not for chasing. Evidence points to an ambush lifestyle relying on short bursts of power rather than extended pursuit. Its sprawling limbs carried it across land, and bone microanatomy shows it was primarily terrestrial, not a true swimmer. It likely hunted at water margins, dragging prey to shore, or patrolled on land for unsuspecting herbivores. Its teeth tell the clearest story. Early species bore smoother blades for simple cutting. Later forms developed serrated steak knife-style cheek teeth capable of slicing flesh with efficiency. At the front of its jaws stood long canines perfect for spearing prey or clamping down on amphibians like Eriops. Along the flanks, recurved blade-like teeth tore meat into manageable strips. Near the back, thicker teeth helped crush through bone or scales. This arrangement, known as heterodont dentition, was rare for the time and gave Dimetrodon a versatility many predators lacked. Fossil discoveries reveal diversity within the genus itself. Some species carried delicate teeth tailored for smaller fish or amphibians, while others wielded robust cutting edges for larger terrestrial prey. This spread of adaptations meant Dimetrodon as a group filled multiple hunting niches, amplifying their influence across ecosystems. They were not single-strategy hunters, but a family of apex predators, each variation tuned to dominate specific conditions. Meals could range from bulky amphibians to small reptile herbivores. For the victims, a single encounter was usually fatal. Dimetrodon's ambush-powered jaw strength and complex weaponry offered few chances of escape. Flexibility was its edge. As climate shifted and ecosystems changed, its diet could shift as well, securing its role as top carnivore for millions of years. Size, heavy build, and specialized dentition defined its supremacy. But for all the attention its jaws draw, Dimetrodon is remembered today for something else. Its most recognizable feature was not inside its mouth at all, but on its back, a towering sail that made it impossible to mistake. The sail itself is where the real puzzle begins. Rising from the backbone, it was built from dramatically elongated neural spines, each sheathed in tissue and skin. Fossil evidence shows grooves and periosteal features on the bone surfaces where soft tissue and blood vessels likely attached, but these spines lack the large internal vascular canals once thought to exist. That means the sail was not the highly vascularized solar panel early reconstructions imagined, though some circulation was almost certainly present. This nuance shapes how scientists think about what the sail actually did. Three major hypotheses dominate the debate. The first is thermoregulation. With its wide surface area, the sail could have absorbed warmth in the cool morning or shed heat under a strong midday sun. In theory, this might have allowed Dimetrodon to become active earlier than its prey. However, later, modelling studies have questioned how effective this really was. The efficiency would have depended on sail size relative to body mass and surrounding climate conditions, and not all species of Dimetrodon had large sails. For smaller varieties, the surface area may not have meaningfully influenced body temperature. So while thermoregulation remains possible, the evidence is mixed. A second idea emphasizes display or sexual selection. In some specimens, the sail shows positive allometry. It grew disproportionately larger compared to body size. That kind of scaling is common in structures used to attract mates or intimidate rivals. In modern animals, think of a peacock's fan of feathers, a lion's mane, or the throat frill of certain lizards. A tall, striking sail could have signaled health fitness or dominance both to potential mates and competing predators. The disproportionate growth of the sail strengthens this possibility, suggesting it carried a social or visual role beyond mere physiology. The third hypothesis includes other possible functions such as intimidation of rivals or added stability when moving. Some researchers point to convergent evolution for support. The herbivorous Edaphosaurus, a distant relative of Dimetrodon, independently evolved a very similar sail. When two unrelated lineages converge on the same feature, it usually signals consistent selective pressure. The exact role may not have been identical in both animals. What helped one species communicate or thermoregulate might have helped the other in a slightly different way, but convergence suggests the sail solved a recurring challenge in the early Permian environment. Taken together, the sail was probably multi-purpose. It could have contributed to body temperature control, but evidence increasingly leans toward it being a prominent visual signal as well. Rather than a single answer, its function likely blended physiology with communication. For Dimetrodon, that meant an outward marker that made it impossible to mistake in life as much as it is today in museums. And when you consider the total picture of this animal, the sail was only part of why it mattered. Its role in deep time went far beyond its unusual backspines. Dimetrodon stands as one of the great reminders of how deep Earth's story runs. It wasn't a dinosaur at all, but an early synapsid that lived tens of millions of years before them. Its body carried features that hint at mammal-like traits, heterodont teeth, a single temporal opening in the skull, yet it was not a direct ancestor of mammals. Instead, it represents a parallel branch successful in its own right. Keep 3 points in mind: it predates dinosaurs by over 40 million years, it reigned as an apex predator with size and specialized teeth, and its sail remains a debated but likely multi-purpose structure. Which sail function do you find most convincing thermoregulation or display? Tell us below, and don't forget to like and subscribe for more deep time stories.